VHS 1256b emits no starlight. The red veins of heat illuminating its atmospheric bands are generated entirely from within its own interior. Located in the constellation Corvus, roughly 70 light-years from Earth, this object exists in near total isolation. At approximately 19 times the mass of Jupiter, it sits squarely in the mass threshold of a brown dwarf. It is too massive to be a standard gas giant planet, yet lacks the mass required to ignite sustained nuclear fusion and become a star. It orbits a binary pair of stars at a distance of 350 astronomical units. At that extreme range, stellar radiation provides virtually no ambient heat to its atmosphere. Despite this distance, spectroscopic measurements reveal an atmospheric temperature of 1300 Kelvin. Without a nuclear fusing core, a conventional planet in this orbit should be frozen. Instead, we are looking at a self-contained thermodynamic system. To understand how a non-stellar object maintains such extreme thermal output, we have to look past the surface and examine the mechanics of the core. VHS 1256b operates as a substellar engine, driven entirely by the ongoing physics of its own gravitational and thermal history. The primary energy source here is gravitational compression. As the object's massive gas layers press inward, the sheer mechanical crushing force converts potential energy into immense kinetic heat at the center. This heat was generated during the brown dwarf's initial collapse millions of years ago. Because the thick outer atmosphere acts as an incredibly effective insulator, that primordial energy remains trapped, only slowly leaking outward over billions of years. This creates a steep thermal gradient. Deep in the interior, temperatures reach thousands of degrees, gradually cooling to a dull red as the energy propagates toward the upper atmosphere. The result is an ongoing mechanical battle. The outward push of thermal pressure violently fights against the constant, massive pull of gravity. In smaller gas giants like Jupiter, cooling leads to a relatively static, equilibrium-based atmosphere. Here, the internal heat is too high, and the thermal gradient is too steep for the gases to settle. The mass of the object itself acts as the engine, sustaining a permanent state of boiling turbulence from the inside out. Determining the composition of that turbulence required capturing faint infrared signatures emitted by the brown dwarf, a task executed by the James Webb Space Telescope. Webb used its MIRI and near-spec instruments to isolate target wavelengths between 1 and 20 microns. By analyzing this light through spectroscopy, researchers can read the absorption lines, the exact molecular fingerprints of the gases blocking the internal glow. The data quickly confirmed the presence of methane and carbon monoxide, standard compounds expected in the models of large, hot gas giants. But the spectrum also revealed a distinct outlier, the chemical signature of solid silicate particles suspended high in the atmosphere. This flux data distinguishes between first-light objects and substellar anomalies. Mapping mid-infrared light drops confirms specific solid matter within the gas. Capturing this required the precise assembly of the mid-infrared instrument, utilizing specialized detectors for extreme spectral sensitivity. The instrumentation proved the ratio of carbon monoxide to methane did not match standard equilibrium models. The gases were actively mixing at speeds that defied chemical settling. JWST's hardware confirmed a startling physical reality. High-altitude minerals were forming in an atmospheric layer where none should naturally exist. Deep within the interior of VHS 1256b, temperatures exceed 830 degrees Celsius. Here, rock does not exist as a solid surface, but as a superheated, vaporized gas. Driven by the internal engine, this vaporized rock is forced upward through massive, rising convection columns. As the gas reaches the lower pressure and cooler temperatures of the high altitudes, it crosses a critical thermodynamic threshold. The rock vapors begin to condense. The primary compounds forming here are silicates, the same basic mineral structures that make up quartz and beach sand on Earth. The rapid cooling triggers immediate crystallization, transforming the vapor into clouds comprised of trillions of jagged, microscopic geometric shards. These silicate particles are highly abrasive, resembling a storm of volcanic ash or pulverized glass. Unlike the gentle condensation of water ice clouds on Earth or the ammonia storms of Jupiter, these are heavy, mineral-based weather systems. The atmosphere of VHS 1256b is essentially an airborne quarry of abrasive, high-velocity minerals. To keep heavy silicates aloft, the planet relies on powerful 3D fluid dynamics, characterized by massive rolling convection cells. Despite its mass, VHS 1256b has a relatively low surface gravity for a brown dwarf. This weaker gravitational pull prevents the heavy glass clouds from immediately collapsing back into the dense interior. Simultaneously, atmospheric upwelling provides a constant mechanical lift. Hot, low-density gas from the interior expands and violently pushes its way towards the surface. This creates enough upward buoyancy to allow the silicate clouds to persist at the very top of the observable atmosphere. The resulting physics are highly destructive. Sinking columns of cold, heavy cloud matter crash directly into rising columns of hot vapor, creating immense turbulence in the interaction zones. The extreme thermal gradient drives these vertical currents at high velocities, constantly dredging material from the deep interior up into the vacuum of space. This relentless vertical mixing is what forces the atmosphere into chemical disequilibrium, preventing any stable separation of gases. The vertical motion alone ensures that VHS 1256b is locked in an environment of constant, violent recycling. There is one final variable controlling the planet's weather. VHS 1256b completes a full rotation every 22 hours. For an object of this mass, that is an incredibly rapid spin. The rotation introduces severe horizontal shearing forces that cut directly across the vertical convection cells. The rotational velocity rips the rising columns apart, smearing the vertical weather systems into chaotic, marbled horizontal bands across the entire circumference. This global shearing effect is directly responsible for the record-breaking 37% variability in brightness observed by JWST over a single rotation. Because the weather is torn into patchy clouds rather than uniform layers, our telescopes see deep into the hot, bright interior in some regions, while other areas are blocked by dark, cold silicate storms. The churn drags deep-layer carbon monoxide up into plain view, while forcing upper-layer methane down into the dark. The mechanics of the atmosphere operate precisely like an abrasive industrial blender, tearing the planet's own minerals apart at high speeds. The record-breaking variability of VHS 1256b is the inevitable result of its physics, a low-gravity engine spinning its own silicate glass into a permanent global storm.